Hello and welcome to this new example on compressible flow. Also, I've included this example as a PDF file, so please, I really recommend that you pause this video and try to solve this example by yourself. So here, the static pressure to stagnation pressure ratio at a point in a flow stream is measured as being equal to 0.82. So we have P over P naught equal to 0.82. The stagnation temperature of the fluid is 20 degrees Celsius. So T naught is equal to 20 degrees Celsius, which is actually equivalent to 293 Kelvin. Determine the flow velocity if the fluid is considered as air in part A and as helium in part B. So for air, take K equal to 1.4 and the gas constant equal to 287 joule per kilogram Kelvin. However, for helium, K is equal to 1.66 and R is equal to 2077 joule per kilogram Kelvin. So let's start with part A. So to find the flow velocity for air, we will say that V is equal to the Mach number multiplied by the speed of sound, which is equal to radical kRt. So to find V, we need first to know what is the Mach number and what is the value of the temperature T. So since we're dealing with air here and we know the pressure ratio P over P naught, we can go ahead and open the compressible flow tables.pdf and look at table B1. So please pay attention that table B1 is only valid for a perfect gas where K is equal to 1.4. which is the case here in part A, since we're dealing with air and air has K equal to 1.4. So using this table is completely a valid option. However, you should be careful that you cannot use this table to calculate the flow velocity for helium, because helium has K equal to 1.66. And in fact, you need to rely on the equations that we have developed previously to solve for the flow velocity of helium. So for air, we know P over P naught equal to 0.82. So if you search in column number 2 and you scroll down, you can find this row here. P over P naught is 0.8201, which is approximately the case here. So at this pressure ratio, the Mach number is equal to 0.54. And to find the temperature, we need to search for the temperature ratio, T over T naught, which is equal to 0.9449. So also from the table, T over T naught is equal to 0.9449. And since we know the stagnation temperature T naught, you can find the temperature. So the temperature 0.9449 times the stagnation temperature, which is 293, which is equal to 276.86 Kelvin. So the velocity V will be equal to the Mach number into the square root of K into R into the temperature 276.86, which will be equal to 180 meters per second. Now let's solve part B. So since we will be dealing with helium and helium has K equal to 1.66, actually we cannot use table B1 as we said, since table B1 is only valid for a perfect gas with K equal to 1.4. So let's minimize this window here and we will use the same procedure. So we need to find the Mach number and the temperature for helium, and we will use this equation here to find the flow velocity. So to find the temperature, we will apply the isentropic relationship between the pressure ratio and the temperature ratio. So we said that P over P naught is equal to T over T naught to power K over K minus 1. So to find T, we need to raise to the power K minus 1 over K, both sides. So we will have T over T naught is equal to P over P naught to power k minus 1 over k. So T will be equal to T naught, 293, into the pressure ratio, which is 0.82. So be careful that K here is equal to 1.66. So K minus 1 is 0.66 over 1.66. So the temperature of helium will be equal to 270.77 Kelvin. Now, to find the Mach number, remember that in the Mach number relations lecture, we have developed an expression relating the pressure ratio to the Mach number for an isentropic flow. So we said that P over P naught is equal to 1 plus K minus 1 over 2 into the Mach number squared to power minus K over K minus 1. So here we have P over P naught equal to 0.82 equal to 1 plus K minus 1, 0.66 over 2 into the Mach number squared, which is unknown here, to power minus K minus 1.66 over 0.66. So we need to solve for the Mach number. So this is a very simple equation. You raise to the power minus 0.66 over 1.66 both sides, and you rearrange the equation to solve for the Mach number. And of course, you will consider only the positive solution. And since a negative Mach number is meaningless in our case. So the Mach number, by solving this equation, it will be equal to 0.499. So now the velocity V will be equal to the Mach number times the square root of K into R into the temperature, which is equal to 482 meters per second. Actually, there is another method to find the flow velocity here by using also equations. So a second method to solve for the flow velocity of helium is to use the stagnation enthalpy. And as we said, the stagnation enthalpy H naught is equal to H plus V square over 2. So instead of finding the Mach number, you can find the velocity directly from this equation. So the stagnation enthalpy H naught is Cp T naught, which is equal to H, which is Cpt plus V square over 2. So the velocity here will be equal to the square root of 2 Cp T naught minus T. Okay, so to find the velocity V here, we need to know the specific heat Cp. And in this problem only is given K and R. So from K and R, we can find Cp, which is Rk over K minus 1. So 2077 into K divided by K minus 1, which is equal to 5,223.97 joule per kilogram Kelvin. So now the velocity will be equal to the square root of 2 times 5,223.97 into T naught minus T. So T naught is 293 minus T, which is equal to 270.77. 270.77. So also you will have the same value, 482 meters per second. So in this part, you saw two ways of solving for the flow velocity. One is by using the Mach number relationship, and from the Mach number you can find the velocity. And the second way, you can use the stagnation enthalpy and you can solve directly for the velocity. And in both cases, you need first to find, of course, the temperature by using the isentropic relationship between the temperature ratio and the pressure ratio. So please, the important point here in this example is to know when to use the table. So as you saw, we can only use the table when we have K equal to 1.4 as in part A. However, for the helium, since K is equal to 1.66, we cannot use the table, and we have relied on the equations that we have developed previously to solve for the flow velocity v. So now we have finished this problem. In the next lecture, we will start to talk about the effect of the area change on the Mach number and on the properties of ideal gas, mainly the pressure variation and the temperature variation with respect to the area variation. So let's see how to do this in the next lecture.